Yes. This was a big one, you guys. Transformations. Transformations of functions. The main point of this is to graph. There's going to be a lot of graphing in this section. Okay, we need to talk about vertical and horizontal transformations. We need to talk about vertical and horizontal stretch and compression. We need to talk about reflecting and last, and don't let me forget this, sometimes I forget about this topic, even versus odd functions. Oh, by the way, please listen carefully. I did make an amendment to your homework, your list of homework problems for this section, particularly 2.5. I added some more problems onto it. For some reason, I did not include problems on the one that's on the website. There weren't any problems on even versus odd functions, and it is going to be on the test. So I'm going to update the website. If you printed off a list of problems, throw that away and print off a new list of problems. Okay, 2.5 has changed. So, before we get into objective 1, let's do a little background. Quick little background. You need to be familiar with the shape of different graphs. Parent functions is what they're called. I think all of these you've seen before, but let's just make sure. So first parent function we're going to look at, y equals the absolute value of x. It's a V-shaped graph. The vertex is at the origin. Spot coming up like that. And a part coming up like that. That is the absolute value of x, the parent function. Okay? x1. Y equals x squared. You guys know that one. What's the graph of y equals x squared? It's a parabola whose vertex is at the origin again. Another one that you're going to need to be familiar with for this particular lesson, y equals the square root of x. You need to be familiar with its graph. That one has a starting point at the origin 0, 0, and it kind of heads off in that direction. That's the square root of x. You're also going to need to know, let's see. That's really about it. Let's do one more. You might need to know this one. Y equals the cube root of x. Yeah. Yeah. This one's a little bit harder to draw. It has the middle point right here in the origin. There's a piece that comes. There's a piece that comes off like that. and a piece that comes down like that. That's y equals the cube root of x. Now, let's get into objective 1. Horizontal and vertical transformations. And we'll start with horizontal. So to graph f of x minus c shift the graph of f of x to the right c units. And for f of x plus c, you shift the graph of f of x to the left c units. So here's an example. And you guys have done this before. We talked about it at the beginning of the year. You've done this a ton in Algebra 2. If I asked you to graph f of x equals x plus 2 to the second power. Okay. First of all, what type of graph is this? Which family does it belong to? It belongs to this family of functions called parabolas. These are quadratic functions. The parent function looks like this. Y equals x squared has a vertex at 0, 0. Okay. We've got to figure out what type of a shift this is. Since it is inside of the function, this is considered, I use the phrase here, inside. This is inside the function. F of x plus c means plus c is considered a transformation that occurs within the function. Same thing here. Is this number part of what's being squared? Yes. Yeah, so that's considered inside the function. Had I asked you to do this, I don't want you to write this down because it might confuse you when you use your notes later, but had I asked you to graph this, is the plus 2 considered part of what's being squared? No. So it's not the same transformation as this. Okay? So according to what we have written as a definition, this is x plus 2. What direction does that move the graph? To the left by that many units, in this case 2 units. So the graph of f of x equals x squared, remember, just looks like a parabola with the vertex at the origin. We've got to compare that to what we want to graph here. F of x equals x plus 2 squared. What's the difference going to be?
3 units to the left.
The vertex. Yeah, pretty much is going to be the only difference. It moves 2 units to the left, so there's your vertex. But the shape of the graph, what's the shape of the graph still going to be? Still going to be a parabola. Now you need to be a little bit more exact. I'm not going to accept just a vertex and then some randomly drawn parabola on a test. You have to be more exact than that. So you have to choose some x and y values that go on the graph. We already know one point that's on the graph. It's -2, 0. That's your vertex. So let's plot another point. I want a point near that. -4 would work. Can we go even closer though? -3 or -1 would be even closer. So let's do -3. -3 plus 2 is -1 squared is 1. So -3, 1. And that's actually sufficient. Why? What's special about a parabola? it's the same on either side, right? It's symmetric. So this point that we just plotted gets reflected to that point over here. And those are the 3 points you need to graph your parabola. We're graphing using what are called transformation techniques. Now, question for you. Why, if it says x plus 2, why in the world would it move to the left? Because most students, when they see something like that, they think, okay, x plus 2, that's got to go to the right. Why does it have to move in the opposite direction? Yeah, it is. Why does that mean it has to behave opposite, you guys?
Because it's inside the parentheses. If you take it out of the parentheses, or you, I don't know exactly what it's saying.
It is really hard to explain, actually. Why does it move opposite? Conventional wisdom might think, okay, this has got to move to the right, because isn't this positive 2 over here? Why does it move opposite of that? Here's one explanation of why that is. Okay? What's the point right here, you guys? What's the location of that point? It's negative 2 comma 0. What kind of a number is this right here, an x or a y number? It's a y number, correct? So f of x is the same as y. So if I replace that with a 0, what does this value have to be in order to make sure that this is 0? This value of x has to be negative 2. So in order to maintain a value of 0 for the y part, the graph has to move over to allow x to equal negative 2. Does that make sense?
Yeah.
Because what's negative 2 plus 2? 0. So the graph has to move over to negative 2 in order to have a y value of 0. That's why it moves opposite. Okay, that's one explanation of why. Let's do another one. Part B. Graph f of x equals square root of x minus 3. This is a change that occurs within the function, the square root function. So this is another one of these horizontal shifts, and you have to be able to distinguish the difference. Had I asked you to graph this, would this have been totally different? Yeah, because this is not within the function. Okay, this is inside the function. Okay? The phrase inside the function is opposite is really what you need to remember here. Inside the function is opposite. X minus 3 moves it in which direction? To the right. You do have to remember what these types of graphs look like. Square root of x, y equals the square root of x will be a graph that looks like this. Starts at the 0, 0 and kind of comes off to the right. So this graph's going to have the same shape as this, just starts in a different point. Go over 3. So it starts there at the point 3 comma 0, but again, I'm not just going to accept a starting point and then a randomly drawn graph like that. It needs to be more exact. So we know that 3 comma 0 is on the graph. What are some other points we could choose? 7, let's see. Why 7 specifically? 7 minus 3 is 4. And 4 has a nice square root. So 7 is a great number. 7 minus 3 is 4. Square root of 4 is 2. So 7 comma 2. 1, 2, 3, 4, 5, 6, 7. 7 comma 2. We skipped one. There's a number between 3 and 7 that will work well. 4. 4 minus 3 is 1. Square root of 1 is 1. So 4 comma 1. So there you go. Ooh, let's extend your understanding of this. What's the domain? Bracket or parenthesis? Bracket. 3 to infinity. Now, you could have found that out just by looking at the graph, or remember, this is something the students forget on exams. If I had just given you the equation and you didn't know the picture of the graph, how would you find the domain of just that function? Yep. X minus 3 has to be greater than or equal to 0. Add 3 to both sides, and x is greater than or equal to 3, which is 3 to infinity. Okay, range is 0 to infinity. All right. Are we good on horizontal shifts?
Yes.
Okay. Let's go to vertical. This one. Vertical shifts. The change occurs outside of the function. So to graph f of x plus c. Now take a look at where the plus c occurs, you guys. Is that inside or outside?
Outside.
This is outside of the function. So to graph f of x plus c, move Gesundheit. Graph of f of x up c units. Okay. To graph f of x minus c, you move the graph of f of x down c units. Okay, imagine this in your mind, you guys. You ready? I guess where else could you imagine it? That was kind of redundant. Imagine this in your minds. Anyway, what's another way to describe f of x? Isn't it just y? So f of x represents y values. Are you thinking about this? If I add a number c to all of the y values in a graph, what's going to happen to the graph? It's going to move up by that amount of units, by c units. If I take all of the y values and subtract by c, what's going to happen to the graph? It's going to move down. That's why this is represented by a vertical shift, moving up or moving down. So not to spend a lot of time on this, I think you guys have a pretty good handle of this already. Example 2, though. If I asked you to graph f of x equals the absolute value of x minus 4 you always need to determine where this transformation occurs. Would you describe this as inside or outside of a function? Outside of a function. So that follows this definition right here. This is a vertical shift. Since it's minus 4, it's going to shift the graph down. So you have to have in mind what the actual parent function graph looks like. If I ask you to graph y equals the absolute value of just plain x, it's a V-shaped graph whose vertex is at the origin like this. So absolute value of x minus 4 the vertex has been moved down 4 units. Okay. Has the same basic shape as this one. We've got to find some x and y points. We know that one point is 0, negative 4, so let's let x equal 1. These graphs are symmetric as well. Absolute value of 1 is 1, minus 4 is negative 3, so 1, negative 3. That point gets reflected to negative 1, negative 3. You like how incredibly straight those lines are? Man. We good so far? Okay. Let's move on. The next objective was what? Ooh, stretching and compressing. Okay. Here we go. Let's start with a vertical compression or stretch. Given y equals f of x, just some random equation, some random graph. Given y equals f of x, the function y equals a times f of x. A times f of x. Is a vertical stretch if A is greater than 1 and a vertical compression if A is less than 1 but still has to be greater than 0. So A has to be something between 0 and 1. So we need to compare and contrast the differences between this and the other vertical change, because we had a vertical shift which actually moved the graph vertically. This is a vertical compression and a vertical stretch. So it doesn't actually move the graph, it stretches it vertically or it compresses it vertically. And why is that? Well, first take a look at the change that occurs. Would you describe this number A here as inside or outside the function? Outside. Now, look back up in your notes for a second. On the vertical shift, wasn't this also outside the function? Yeah. So any change that occurs outside the function, you guys, you got to keep this straight. How does it affect the graph? Horizontally or vertically? Vertically. Anything that occurs outside the function is a vertical change. But why is this called a vertical shift, whereas this one right here is called a vertical compression? And it has to do with the operation separating the number and the function. What is A doing to the graph? Multiplying it. Here, what's it doing? Adding. That's a big distinction. Okay? If there's number outside the function that's multiplying, that's a vertical stretch or compression. If it's adding to the function, it actually moves the function up or down, but it doesn't affect the shape. These compression and stretches affect the shape of the graph, not the location of the vertex. So for example, let's consider example 3. So the graph y equals 2 times the square root of x. Now I actually do want you to draw this one so you have something to compare it to. And make it the same size as the other graph that we're going to draw. So let's graph first y equals the square root of x. Do you remember what this graph looked like? Just square root of x. Where does it start? 0, 0. And then if you plug in a 1 for x, what do you get for y? So 1, 1. If you plug in a 4 for x, what do you get for y? It's okay. Now I also want you to do this to have some more data to compare it to. Let's make a list of values. We have 0, 0, we have 1, 1, and we have the point 4, 2. So these are some points on the parent function. This is the graph of a parent function. How does that then compare to the graph of y equals 2 times the square root of x? First of all, does this change occur within the function or outside the function? Outside. So how is it going to affect the graph? Vertically. And the 2 is multiplying the function. It's not adding to the function. So that's this kind of a transformation, yes? A times f of x. Had I done this, you guys, what kind of transformation would that be? If it was 2 plus the square root of x, what would you do? It's not a stretch or compression. Now it's just a vertical shift up 2 units. But what I had here is 2 times the square root of x. So that represents a vertical, well, is it a vertical stretch or a vertical compression? Stretch. A is greater than 1. So it's a vertical stretch. That's not going to affect the location of the graph. It affects the shape. So the graph is still going to start at 0, 0, but what's going to happen is the graph is going to be stretched out vertically. Okay? So it's going to appear to rise much quicker and have a little bit steeper of a change in its direction right here. How do we do this? We could plug in some points, you guys. I want you to consider this, though. Here's maybe an easier way to think about this. Could we think about this as y equals 2 times f of x? What's another way of saying f of x? Isn't f of x just y values? So what this is saying is your new y values are going to be 2 times the y values of the parent function. This is the parent function right here. So our new graph is just going to be 2 times all of the y values of this original function. Are you following me here?
Yeah.
So if we take this table of values right here and rewrite it over here, which column gets multiplied by 2? The y column. Because here it's saying 2 times f of x, which is 2 times y. So we double all the y values. And we keep the x values the same. So we're going to have 0, 1, and 4. But what happens to the y? 0? 0 stays the same because 0 times 2 is 0. What about this 1? The 2 and the 4 and the 2 over here becomes 4. All we did is take the y column and double it. So now we have some points we can plot. Zero comma 0, 1 comma 2, and 4 comma 4. So the graph is in the same location, yes? What's changed about the graph? It's been stretched. It's like somebody grabbed the graph and stretched it vertically. Okay? Let's take a look at one more fairly common graph. Let's do part B. I want you to graph y equals 1/2 times x squared. 1/2 times x squared. Now, with square root functions, it's really easy to determine whether the change occurs inside or outside the function. Sometimes with these x squared functions, it's not quite as easy to tell what's inside the function and what's outside. You have to determine what the function is. The function is a squaring function. Anything that's being squared is considered inside the function. Is the 1/2 being squared? No, so it's outside of the function. But had I done this, wouldn't that be something completely different? Now 1/2 is part of what's being squared, so this would be considered inside the function. But as it was, I want you to graph 1/2 x squared. So consider then what the parent function looks like. It's got a vertex at 0, 0. It has a point at 1, 1. It has a point at 2, 4. And then directly opposite, negative 1, 1 and negative 2, 4. If we listed those points on a graph, we have negative 2, negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. Those are points on the parent function, y equals x squared. Another way of thinking about this is to graph y equals 1/2 of f of x. X squared equals f of x. I'm asking you to graph 1/2 of f of x. Well, what are f of x values? They're the same as y values. I'm asking you to graph 1/2 of all the y values. The x values stay the same. X values are not affected. You need to graph 1/2 of the y values. So if we're making a table of values from the original function here, which column is affected? The y column. I'm asking you to grab 1/2 of f of x. F of x are y values.
Can you Stephen Robbins to the front office?
Okay. So the x column is going to stay the same. Negative 2, negative 1, 0, 1, and 2. What happens to our y column? Tell me the values quick, you guys. We're running out of time. This point becomes what? Whoa, that was weird. I just drew a perfect pentagon. This point becomes negative 2, 2. This point right here becomes negative 1, 0.5. This point still stays 0, 0. This point becomes 1, 0.5. And this point here 2, 2. So now we have some points to graph. By the way, what kind of effect is this? A vertical stretch or vertical compression? Compression. So if you can imagine that parabola over there in blue and somebody taking it with their hands and smashing it down vertically, it's gonna look to be a little bit fatter, right? Or more wide. So plotting the points. -2, 2. -1, 1/2. There's a graph of y equals 1/2 x squared. Let's talk for a minute about horizontal compressions and stretches. So given a graph of a parent function, y equals f of x, y equals f of b times x. Now how would you describe that? In or out? It's inside the function. B times x is inside the function. Okay? F of bx is a... Now if it's inside the function, how does it affect the graph? Outside affects it vertically, so inside has to affect it horizontally. So b times x is a horizontal. Now I'm going to leave a blank here for a second. It's a horizontal blank if b is greater than 1. Now I'm just curious as to your thoughts. What would you put in here for this blank? Just the first thought that comes to your mind. If b is greater than 1, would you call this a horizontal compression or a horizontal stretch? You would say stretch, right? But you got to think about back here when we talked about, where is it? Right here. When we talked about horizontal shifting, if it was x minus c, what direction did that actually move it?
Right.
To the right. Isn't that opposite of what you might think? If it's x plus c, it moved to the left. What's that phrase I always say? Inside the function is opposite. Opposite. So let's try this again. If b is greater than 1, I know conventional wisdom says, well, that's just going to stretch the graph horizontally. It's going to get longer horizontally. But what's the opposite of that? Actually a compression. If b is greater than 1, what that actually does is compresses the graph. Okay, horizontally. Okay. And if b is less than 1 but greater than 0, well, that's weird grammar. And 0 greater than b less than 1 is a horizontal stretch. So here's example, I think we're on example 4. And I want you to graph y equals two x raised to the second power. So let's first describe what kind of transformation this is. Is this inside or outside? Inside. This transformation right here is inside the function. Let's consider the parent function real quick. I know we just graphed it, but I want to have it again on there. So this is the parent function of y equals x squared, which has these following points. Negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. How does that then compare to y equals 2x raised to the second power? Now you could argue, well, let's just simplify this and evaluate the exponent. I want to leave it how it is, okay, to illustrate better what happens when a transformation occurs inside the function. Now, just reading that, what does that say to do to all of the x values? X times what? X times 2. So a lot of students think, okay, I'm just going to take all the x values and multiply them by 2. That's wrong. What's that phrase? Inside the function is opposite. What's the opposite of taking all the x values and multiplying them by 2?
By half.
You divide them by 2. Okay? What this means is all x values divided by 2. You have to do the opposite. If it says 2x, the opposite of that is x over 2, or x divided by 2. So if we make a new table of values, the y column remains unchanged. Okay? It's the x column that changes according to this, all x values divided by 2. So what does this point become? Negative 1, comma, 4. There we go. By the way, before we finish this, what kind of change is going to occur here? It is horizontal because it's inside the function. It's going to be horizontally compressed, so it's going to appear to be skinnier. Now, it's very hard graphically to tell the difference. Everybody look up here. If I were to take a parabola and stretch it vertically, what also appears to be happening horizontally? Doesn't appear to be compressing horizontally. Or, if I took a graph and smashed it down vertically, what's also appearing to happen? It appears to be expanding horizontally. Okay, they are different. Algebraically, they're different. Graphically, it's kind of hard to tell the difference. So that's why we're looking at this algebraically, not just graphically. What does this point become? Negative 0.5, comma 1. The vertex stays 0, 0. This point here becomes 0.5, comma 1, and the last point becomes 1, comma 4. So, negative 1, comma 4, negative 0.5, comma 1, 0, 0. 5, comma 1, and 1, comma 4. So doesn't this parabola appear to be much skinnier?
Yeah.
So these are examples of horizontal vertical compressions or shifts. Okay. Let's do kind of a weird example here. Example 5. This is not going to involve a parent function. This is going to involve a uniquely shaped graph. Do your best to draw this graph exactly how I've drawn it. This right here is the graph of some function y equals f of x. It's not a parent function like x squared or square root of x. It's just some random function y equals f of x. Okay. If I ask you to graph y equals 1/2 of f of x. And what's happening here? Is this inside or outside? It's outside. Is it multiplying f of x or is it adding to f of x? And that makes a big difference. Had I asked you to do this, 1/2 plus f of x, what would have occurred there? The whole graph would just move up by half of a unit. Okay, but here I'm asking you to do 1/2 times f of x. So you take all of the y values and do what to them? You times them by 1/2 or divide them by 2. Okay. Well, we don't have an equation to deal with. How do we know what the y values are? We have points on the graph. So what I would recommend for problems like this where they give you a uniquely shaped graph, make a list of some of the easily identifiable points on the graph, some of them that you know exactly where they are. For example, this one is the point -4, 4. Right here. This one here is -2, 0. This one is 0, 2. We have 2, 0. And we have 4, 4. These represent points on the original function f of x. What you should now do is generate a table of values for y equals 1/2 of f of x. Which column gets affected? Yeah, f of x is represented by y values, and we take 1/2 of the y values. So each of these points, their y values get affected. We divide them in half. So the first point becomes -4, 2, and then -2, 0, 0, 1, 2, 0, and last point becomes 4, 2. Now we have a list of points. We can plot those points, draw a new graph. What is the new graph going to look like? What's it supposed to look like? Which direction is it compressed? So it's just going to be smashed down vertically. It's going to be a little bit flatter. So we have -4, 2. We have -2, 0, 0, 1, 2, 0, and 4, 2. Okay, compare the one in blue to the one in black. Is this one in black a vertical compression from the original function? Yeah. All right. We got to talk quickly. We're running really short on time. Reflections. This is not something that we can rush through in 5 minutes. So we're going to have to stop it here.